got a farmer wants to fence an area of 1.5 million square feet in a rectangular field, and then divide it in half with a fence parallel to one of the sides of the rectangle. Farmer wants to fence an area of 1.5 million square feet. Actually, if he's fencing in 1.5 million square feet, I'm not sure if farmer is the proper term. It's probably more rancher. Huge space, right? 1.5 million square feet in a rectangular field, I guess, and then divide it in half with a fence parallel to one of the sides. And then the question is, how can he do this? To minimize the cost of the fence. Okay, so we've got a rectangular fenced area. So that would look like this. And these two sides are the same, so I'll call them both X. And then these two sides are the same, so I'll call them both Y. And then what else is he going to do? Cut it in half with another fence that's parallel to one of the sides. So I have a choice. I can either cut it here with another fence, or I can cut it here with another fence. Doesn't really matter. So I'll do this. So that means the length is X. So apparently he wants to have two separate areas. So he's taking his field, cutting it in half with a third fence. Okay, so this is talking about the cost. And so if we're going to minimize the cost, we need a cost equation. But the problem is there's no information in the problem about cost. So how can we minimize the cost? What are we buying? The fence, right? We're buying the fence. So that means that if we use the least amount of fence, then we're going to minimize the cost. Now that's a little bit different. Yesterday our cost equation, remember our box that we were trying to minimize the cost on? We couldn't minimize the amount of material yesterday because the base was more expensive than the sides. So we needed a cost equation for that one if we were going to minimize cost. But here, all of the fence is costing the same amount. This fence costs the same amount as this fence all the way around. So if we minimize the amount of fence, then we're going to minimize the cost. So I'm going to have F be my main equation, which stands for the amount of the fence. So there's 3 X's that I'm purchasing and 2 Y's. So the amount of fence equation is 3X plus 2Y. So this is our main focus. We need to minimize the amount of fence. But there's a problem because there's 2 variables, right? So we need to go off to the side and do something so that we can get rid of one of these variables. So we have this 1.5 million square feet, which means that the area in here is 1.5 million. So that means x times y is 1.5 million. So he's fencing in 1.5 million square feet. That has to do with area. So that's why this is the area equation. But this is not the main equation, right? This is just a side equation that we're using to help us out. The reason I keep emphasizing that is people get this equation mixed up with this equation. Sometimes people accidentally do the derivative of this one. But since we're not trying to minimize or maximize area, that's why this isn't our focus. We're trying to minimize the amount of fence. So that's why this is our focus. We're just using this to get rid of one of the variables. So I'll divide by x. So y is 1.5 million divided by x. So then you can take that and plug it in over here for y. So f equals 3x plus 2 times 1.5 million divided by x. So f is 3x plus 3 billion divided by x. Or another way to write that is 3 million times x to the negative 1 power. If you divide by x, that's the same as x to the negative 1. Everybody doing okay? Oh, shoot. Okay, so the question wants to know what's the minimum cost, but I'm minimizing the amount of fence to actually minimize the cost. So I need the smallest one of these. And to figure out the minimum of this, you take the derivative, set it equal to 0 and undefined, and go from there. Okay, so you've got to take the derivative of this. So amount of fence prime is 3 minus 3 million x to the negative 2. Derivative of 3x is 3, of course. Then I brought the negative 1 out front, multiplied by the 3 million. So that's why it's negative 3 million. And then subtract 1 from negative 1, you get negative 2. So rewriting this, it would be 3 minus 3 million over x squared. And we're setting that equal to 0, and also equal to undefined. So when is it undefined? When x is 0, good. Because you can't divide by 0. And then solving this, I'm going to take this negative and add it to the other side. So it'll say 3 equals 3 million divided by x squared. Then you multiply both sides by x squared. So that's 3x squared equals 3 million. Then you divide by 3. So x squared is 1 million. Then you take the square root. And you get positive negative 1,000. Okay, so probably this is our min, but we have to confirm for sure whether it is or not. You can't just assume that the answer you get is the min. So you come over here to prove that it's the minimum. So we've got 0 as a critical value, and 1,000 as a critical value, and negative 1,000 as a critical value. Now on this problem, how do you feel about negative numbers? They don't make any sense, right? Because the farmer, unless he lives in some bizarro world, he's not going to have a fence that has a negative side on it. Okay, so we're going to just ignore all the negative numbers. We just need to worry about 0 to infinity. So that's nice because we've only got 2 areas to test that. So I'm going to plug 1 into f prime, and that'll come out to 3 minus 3 million divided by 1 squared. So that's 3 minus 3 million, which is clearly negative, right? It's negative 2,999,997. Just subtracted 3 from 3 million. So it's negative from 0 to 1,000. The derivative is negative from 0 to 1,000. Then I strongly suspect that the derivative is going to be positive past 1,000, right? Because as long as it is, I have a going down and going up, so it's going to be a min. But I can't just assume that, so I plug in 2,000. Plugging 2,000 in for x. I'm going to have to take 2,000 squared. 2,000 squared is 4 million. Just because 2 times 2 is 4, and then 3 zeros times 3 zeros is going to be 6 zeros. So this is 3 minus 3/4. All the zeros would cross out, and that could reduce to 3/4. So it's 2 1/4. 2.25, which is positive. Okay, so as we suspected, the graph of f, the amount of fence graph, is going down, and then it's going up. And so that makes 1,000 a local min. But also, since it's always going down, and then always going up, that makes it an absolute min as well. That's what we're really looking for in this problem, is the absolute min, because the question says, what is the minimum? It doesn't say the word absolute, but the minimum is the minimum, the overall minimum. So the minimum occurs at x equals 1,000. Then the question is kind of vague. It says, how can he do this? So I guess we have to give him short instructions on how to build the fence. So what he should do is, one side should be 1,000 on his rectangle, right? And then how can we figure out what the other side should be? Like back here, if the area is going to be 1.5 million, I could take 1.5 million divided by 1,000 to figure out what the other side is. So build a rectangular pen that is 1,000, what do we got, feet? Yeah, 1,000 feet by 1,500 feet. So I got that 1,500 just by taking 1.5 million divided by 1,000. And then he needs instructions on, remember we had a choice, we could have put the fence parallel this way or parallel this way. But he should, the third fence, the extra fence, should be parallel to the 1,000. At that point, if we said this much, the farmer might be a little bit insulted because nobody is going to accidentally take the 1,000 and put it there, right? So, but anyway, I'm trying to be exact, so. Everybody good? Yeah.
So this is the first derivative test that we're using.
Yes, which is kind of weird because the first derivative test is a test for locals.
Yeah, so are we just getting lucky with these problems?
We are sort of just getting lucky, and that what's happening is there's only one critical value. And so if it goes down and comes up and doesn't turn anywhere else, then that local also happens to be an absolute. There's a bunch of specialized cases, you know, so, but this is one specialized case where the local happens to be an absolute. But that's a good comment because the first derivative test is usually a test for locals, not for absolutes.
So if there were more critical values, we would have to use the closed interval method.
Well, then that gets a little bit awkward because this isn't a closed interval. It's 0 to infinity. So, yeah. There's not an exact science here. You just kind of have to look at your chart and logic it out on the individual problem. So I want to look back at the box that we made yesterday. It was example 3. Remember we got to the cost equation, but we didn't get a chance to actually find out the minimum cost. So I think the cost equation was like 1.25 xy plus x squared or something. Am I on the right track there? I thought we multiplied the 0.5 times 2, though. Maybe I didn't do that. I should have.
25 cents.
Oh, yeah. Okay. All right. Cool. Good. Yes. Thank you. So it's 1.25 xy plus 0.5 x squared. Okay. So that's the cost equation, right? So then how would we find the minimum cost? Yeah.
Find the local max of that, like was the first derivative test.
Yeah, take the derivative of it, set it equal to 0 and undefined, and go from there, right? The algebra on that problem is similar to the algebra on this problem. So it's okay that we didn't go through it. Oh, sorry, before we do that, we need to get rid of the y, right? I got a little bit farther other periods, so I'm... Oh, we did? Okay, so we got the x to the -1 in our formula, right? So you see why it's similar to this type of equation here? So the algebra would be similar, so that's why it's okay that we didn't get through it. But I wanted to tell you the answer. It turns out that in case you want to go through this problem at some point, you don't have to, I'm not saying you have to, but anyway, the answer is the minimum cost is $600. Which it's too bad I didn't get to that yesterday because let's take a minute and realize this. This is a box, and the minimum cost is $600. So this is pretty expensive. It must be made out of pure gold or something. And then one year somebody commented, it doesn't even have a top on it, and it's costing $600. That's crazy. So I wouldn't suggest. Maybe it's a really nice box. You can buy it for your mom for Christmas or something, but maybe you should get a top put on. Anyway, I wanted you to have the answer since I didn't get to the answer yesterday. But it's not, it's very similar to this type of problem. Is everybody doing okay? All right, moving on to the next one. So this time we're going to make a poster, and we've got some specifications that they have been given to us. A poster should have an area of 180 square inches, and it's going to have 1-inch margins. At the bottom and sides. And a 2-inch margin at the top. So we're designing a poster, and someone told us that it should have an area of 180 square inches. And 1-inch margins at the sides and bottom, and a 2 extra margin at the top, a 2-inch margin at the top. And what we're going to figure out is what dimensions give the largest printed area. What dimensions give the largest printed area? All right, so I'm going to start drawing this poster. Here's the overall poster. And then there's printing in the middle of it. And so it kind of looks like this. So there's a nice white border around it. And the margins at the bottom and the sides are 1 inch. So this margin is 1 inch at the bottom. This margin is 1 inch. That margin's 1 inch. At the top, though, it's a little bit wider. 2-inch margin at the top. So I've been doing this problem for 6 or 7 years in class. And last year was the first year somebody noticed that this is exactly like the Johnny Bench poster over there. So that poster was up there for 6 years, and I did this problem 6 years and nobody ever noticed, but anyway. So you see the skinny margins on the side there, and then up above the word Johnny is a larger margin. That's what's going on. All right, so the question's talking about the largest printed area. So the printed area is this. So we're trying to maximize that area. But I don't know what the larger part is, so I'm going to call the width of the overall poster X and the height of the overall poster Y. And I know the overall area is 180 because it says the poster should have an area of 180. So if I pick this to be X and that to be Y, that means X times Y is 180. But this is not my main equation, right? Because I already know what this is. This is 180. I can't maximize this because it's a fixed 180. What I'm trying to maximize is not the overall area. This is the overall area. What I'm trying to maximize is what the printed area is. Because the question says, what's the maximum printed area? So this is my focus, my printed area formula. So I need to figure out how far it is from here to here, and also how far it is from here to here, so that I can multiply those to get my printed area. So this is x. So this is x from here to here. And I subtracted 1 over here, and subtracted 1 over here. So this width is x minus 2. Is everybody okay with that length, that width there being x minus 2? And then how about the distance from here to here? What's that? Y minus 3. Everybody good with that? Because I subtracted 1 on the bottom and 2 on the top. And then if you take the x minus 2 times the y minus 3, that'll give you the area inside there. So I'm going to FOIL that out. So that gives me xy minus 3x minus 2y plus 6. But I'd rather not have two variables. So that's what this equation is for, using this to get rid of one of the variables. So solving for y, that's y equals 180 over x. I can take that, plug it in over there. So printed area equals x times 180 over x minus 3x minus 2 times 180 over x plus 6. So here the x's will cancel, so we just have 180 minus 3x. 2 times 180 is 360, so that's 360. I'll go ahead and make that x to the negative 1. So there's my printed area equation. So then I got to maximize that, right? Notice no calculus happened until this point, which is kind of annoying, right? It's a lot of thinking to not be calculus. But if I'm going to maximize that, I need to take the derivative, set it equal to 0, not defined, etc. So printed area prime. Derivative of 180 is 0. Derivative of negative 3x is negative 3. And that would be plus 360 x to the negative 2. So it's undefined when x is 0. Because this is divided by x squared, right? And then I can set it equal to 0. Add the 3 to the other side. Multiply by x squared. divide by 3. And then take the square root. So then you gotta slap that on a number line. I'm ignoring the negatives again, right? But I got a test. So printed area derivative at 1 is negative 3 plus 360 divided by 1 squared. So it's 357. So that's positive. And then printed area prime at, I just got to make sure I'm bigger than 120. So I guess I'll go with, I think 100 is bigger than the square root of 120. So negative 3 plus 360 divided by 100 squared. Squared is 10,000. That's why I picked 100, because I squared my head. .360 10,000ths is 0.360. So at any rate, it's going to be negative, right? Which is good news, because that makes this a max, which we were hoping it would be. So we got x equals the square root of 120. Then the last thing you got to watch out for is make sure you answer the question. So this question says what dimensions give the largest printed area? Dimensions are the length and the width. So we've got the length so far, or if the width, whichever you want to call it. So then we can just plug that into y equals 180 divided by that. So here's the other side of the poster. 180 divided by square root 120. So then that gives both dimensions, right? The width and the length of the poster. Yes? It depends on what the question's asking. Like this one's saying, what dimensions? I think it's talking about the dimensions of the overall poster. But if it said, what dimensions of the printed part give the largest printed area, then you'd have, then you'd have to subtract the 2 and subtract the 3. Yes, and I agree that the sentence doesn't necessarily specify that. It just says what dimensions. But I'm interpreting it as the dimensions of the overall poster. Because if you're going to make the poster, that's what you would cut out. Then later you would draw in the printed area. So you'd have to know those dimensions too. So, yeah. Good. Everybody else good? All right, that's it for today.